Okay guys, we're going to do a really quick intro to sequences. Sequences really don't show up on the AP exam, but we need to have a basic working knowledge of what a sequence is and how to tell if they converge or diverge in order to have some of our discussions when we get to series, which is heavily covered on the BC exam. Okay, so you did some sequences in pre-calc. Sequence is just a list of numbers in a definite order. We use our nice little curly brackets to denote a sequence. We have terms A1, A2, A3, up through A sub n. If we write things this way, that says the sequence of the a sub n's, and we assume that when there's no starting value indicated, that you start at n equals 1. Okay, so this is the official way to write that we start at n equals 1 and we end at infinity. We're talking about infinite sequences, although, you know, you can have a finite sequence as well. So just some real simple examples. For example 1, I gave you guys the sequences of n over n plus 1 from n equals 1 to infinity, and you find the terms of your sequences by plugging in different n values and then incrementing by 1. So I started by plugging in n equals 1. I got 1 over 1 plus 1, or a half. N equals 2. I got 2 over 2 plus 1, or 2/3. Then I did n equals 3. I got 3 over 3 plus 1, or 3/4, and so on. All right, that little dot, dot, dot at the end shows that it keeps going, and if you suck at drawing curly brackets, then keep practicing. All right, for example 2, 3, and 4, I just want you to list me the first 5 terms of those sequences. Pause and come back to me. Okay, so for example 2, we have negative 2/3, 3/9, which you really should reduce to 1/3, but not a big deal. Negative 4 over 27, 5 over 81, negative 6 over 243, which also should be reduced to negative 2 over 81. All right, and I have my dot, dot, dot at the end. It's in curly brackets. I'm good to go. I started at n equals 1 because it didn't say, and if it doesn't say, you start at n equals 1. Try 3, pause, come back to me. All right, you should come up with 0, 1, square root 2, square root 3, 2, and so on. All right, try number 4 and come back to me. All right, I should come up for this one, starting at n equals 0, 1, negative 1, 1, negative 1, 1. This is actually going to be really important because we're going to see this pop up, not necessarily as a sequence, but as part of a series. It's going to pop up quite frequently. And if I have cosine n pi, it's the same as having like a negative 1 to the nth power. It's going to alternate positive, negative. Okay, so it's important that we remember that. All right, for number 5, I've asked you guys to find a formula for that sequence, and pause, and I will list you some possibilities. All right, I've given you guys a bunch of possibilities. You can write 1/2 to the n. I can write 1 over 2 to the n. Those will give me the exact same thing. If I do 1/2 to the first, to the second, to the third, I'll get my 1/2, 1/4, my 1/8. If I do 1 over 2 to powers, I'll get my 1/2, my 1/4, my 1/8, etc. I can actually start this at n equals 0 instead of starting at n equals 1, and then instead of having 1 over 2 to the n, I'd have 1 over 2 to the n plus 1, okay? I could write this a million different ways. I can write it infinitely many different ways, and it would all represent the same sequence. All right, so try for number 6. Pause, come back to me. Okay, I've just listed 2 possibilities here, having negative 2/3 to the n, starting at n equals 0 and going out to infinity, or having negative 1 to the n times 2 to the n over 3 to the n from n equals 0 to infinity. If I wanted to start at n equals 1, then my exponent would have to be n minus 1 instead of n. I could start at n equals 2 by having the exponent be n minus 2. I could start at n equals negative 1 by having my exponent be an n plus 1. I could have a negative 2 to the n on top and a 3 to the n on bottom. Lots of different possibilities. Okay, so just basic plugging in to find terms of sequences and finding formulas for sequences. Some sequences don't have simple defining equations, like if you looked at the population of New Jersey on the 1st of January every year, or if you looked at the digits of pi. A very, very famous sequence that doesn't have a nice defining equation is the Fibonacci sequence. For all you computer science geeks, Fibonacci sequence has a lot of implications. You use it a lot, okay? Fibonacci sequence is recursively defined, meaning that the definition is based on preceding terms. The Fibonacci sequence has the first term 1 and the second term 1. That's what these two say. And then this tells me that every term after that is the sum of the 2 terms that comes before it. Okay, so the first 6 terms of the Fibonacci sequence, I start with 1 and another 1. I add 1 plus 1 and I get 2. I add 1 plus 2, I get 3. I add 2 plus 3, I get 5. I add 3 plus 5, I get 8, and so on. Okay, there's a lot of fun things that can happen with Fibonacci sequence, and we may or may not have time to talk about them in class. Okay, so the next thing I say to you is that sequences can be plotted, and if you plot the terms of the first problem that we did, and the sequence of n over n plus 1 starting at n equals 1, you'll see a pattern happen. So go ahead and plot those terms for me, and pause and come back. And I've done this very crudely, but at n equals 1 I had 1/2, at n equals 2 I had 2/3, at n equals 3 I had 3/4, and so on. It appears that the terms are approaching 1 as n gets larger. So we could say that the limit as n approaches infinity of a sub n would be 1. Okay, and I can see that on my graph. Okay, that the terms of the sequence are approaching 1. Okay, this is going to lead us to a definition. Okay, so that we say that the sequence of the a sub n's has a limit, or the limit as n approaches infinity of a sub n is L. If we can make the terms of the sequence as close to L as we like by taking n sufficiently large. Okay, so if that limit exists, so if we take the limit as n approaches infinity of the general term, and we get a real finite number, then we call that sequence convergent. If the limit does not exist, meaning we get an infinity or a negative infinity, then we say the sequence is divergent. Okay, so I gave you guys 3 problems, 7, 8, and 9, to tell me whether or not I'm convergent or divergent. And the process to this is very easy. Okay, so for number 7, if I want to know if the sequence is convergent, I'm going to take the limit as n approaches infinity of the general term. So limit as n approaches infinity, 1 over n to the 4th, and if I do 1 over really large numbers to the 4th power, I'm going to get 0. Okay, so therefore my sequence converges to 0. Okay, so it's really that simple. For number 8, try it, pause, come back to me. Okay, so for 8, I'm taking the limit as n approaches infinity of the general term, n squared. I'm getting infinity, which is a very large number, and so therefore we say that the sequence is divergent. Okay, so go ahead and try number 9 and come back to me. And I'm seeing now there's a typo there. That's natural log of n over n. So if I take the limit as n approaches infinity, natural log of n over n, you can do L'Hopital's or you can do dominance, and you will get a value of 0 either way, and so therefore we are going to say that we converge to 0. Okay, so finding convergence and divergence for sequences is very basic. Okay, very straightforward. Okay, so just I put in here that traditional limit laws apply. These might help you to evaluate limits, otherwise they're really not too important. They're the same limit rules that we came up with when we were first evaluating limits in AB. Okay, so not going to spend any time on that. The squeeze theorem, I don't want to get into this in too much detail, but we'll talk about it a little bit more in class. But do your best to draw a picture to illustrate squeeze theorem that if I have a b sub n's that lie in between my a sub n's and my c sub n's, and the limit as n approaches infinity of the general term on the a sub n sequence is approaching the same number that the c sub n sequence is approaching, then the limit as n approaches infinity of b sub n would have to equal L. Okay, so do your best, try to make some sense of this, draw a picture to illustrate this, knowing that our b sub n's have to lie in between our a sub n's and our c sub n's. Okay, so think about it, we'll talk about it in class tomorrow. Okay, so this theorem is a direct product or direct result of the squeeze theorem, which we'll talk about more. But if we have alternating sequences, meaning that the terms are alternately positive, negative, you cannot just take the limit of the general term. And instead, for alternating sequences, you need to take the limit as n approaches infinity, the absolute value of a sub n. If you get 0, the sequence converges to 0. If you get any other number, the sequence will be divergent. Okay, I will go draw you a picture in class tomorrow to illustrate why this is so. But for number 10, if I want to, first of all, look at the sequence, the terms of the sequence would be 1, negative 1, 1, actually I would start with a negative 1, negative 1, 1, negative 1, 1, and so on. I can see that the sequence is not going to converge. The terms are alternating between negative 1 and 1. There's no pattern there. I mean, well, there's a pattern, but they're not all converging to a single value. If I take the limit as n approaches infinity of the absolute value of negative 1 to the n, I would be having the limit as n approaches infinity of just 1, which is not 0, and therefore, because this is alternating, this is going to be divergent. Okay. All right, number 11 is another alternating sequence. So if I look at the terms, that's what I have for you to write out the terms of the sequence. But if I just take the limit as n approaches infinity of its alternately positive, negative, I'm going to take the absolute value of it. Okay. And if I take the absolute value of this, I'll have the limit as n approaches infinity of, the absolute value just gets rid of the negative part, so just 1 over n, and this will give me 0, and so therefore the sequence is convergent to 0. So we converge to 0, okay? We'll talk about this a little bit more in depth tomorrow. Okay, last problem. We have the sequence of 1/2 to the n, and I want to know is it convergent or divergent. So let's just look at the terms of the sequence. So write those out for me, please. I have a half, a quarter, an eighth, a 16th. We actually looked at this, but I gave you the terms and you wrote the definition for me. Is it going to converge or diverge? Well, it looks like our terms are approaching 0, so it would make sense for it to converge to 0. Okay, so the question is, when will a number to a power be convergent? Let's make a rule about it. Okay, now if I'm taking a number and I'm bringing it to a higher power, and I want those numbers to all approach the same value, that value would have to be well, either 0 or 1. And I would approach 0 if I'm taking a fraction between 0 and 1. Right? If I take half of a half of a half of a half of a half, my piece is just going to keep getting smaller, or a third of a third of a third of a third of a third, or 3/4 of 3/4 of 3/4 of 3/4. Those values are going to keep getting smaller, versus if I take a number bigger than 1 and I raise it to a higher power, my numbers are just going to grow and grow and grow, and then there will be no pattern to it whatsoever. So our r to the n's are going to be convergent if r is less than or equal to 1, or if it is bigger than -1. Okay, if you think about plugging in those numbers, if you put -1 in for r, you're going to flop back and forth between +1, -1, +, -1. That will diverge. There'll be they won't all approach the same number. But if r is between those two values, if I've got fractions, then will be approaching 0. And if r is equal to 1, then every term will be 1, and the pattern is that they're all 1. Okay, so let's put that together. Okay, our sequence, will approach 0 if our r is some sort of fraction between -1 and 1, and our sequence will approach 1 if our r value is 1. Okay, so hopefully that's a good quick introduction to sequences. The end.